Welcome to this second part in the Activeloop and Deep Lake tutorial. In the first video we looked at how we can use the open datasets that we can find here in the Activeloop user interface and how we could use the Deep Lake Python SDK to stream the data while we were training our detector. Today we're going to look at how we can upload our own dataset and especially how we can use the version control capabilities in Deep Lake to version control the data, to do different commits and to work with different branches. And we're also going to use the Activeloop user interface to explore the different branches and see what are the changes between different commits so that we really can understand how our dataset is evolving. And in the third video, that will be a later video, we will dive more into model evaluation and how we can use the Activeloop user interface to connect our evaluation results and find the worst and the best image samples and so forth. But for now, let's go to our dataset. So the dataset that we're going to base this on is a Kaggle dataset, an object detection classification dataset. So we have a lot of images here which are marked as negative or positive, depending on if they contain any person with a hard hat or a safety vest on them. So the first step is that we're going to download this. I've already done this, and I have it in my training folder here. So here we can see all the different images. And to upload these images, we're going to use the three first letters in the file name, which indicates if it is a positive or negative sample. So I have prepared a script, which is called upload Kaggle. And here we can see that the code is really simple. What we first need to do is that we import Deep Lake. We define the two class names that we want to use in the user interface, while the labels that we're actually uploading are integers. But this is what will be displayed in the user interface. Next, we have in our main code here, we have a glob pattern that will find all the files in our training folder. And we will create a new empty Deep Lake dataset. And then we will create the different tensors in this image dataset. So we have one tensor for images, and we have one tensor for labels, and we have one tensor for the source name, so that we know what image in the Kaggle dataset the image in the Deep Lake dataset corresponds to. And the different age types on these tell how they will be compressed. And compressing, of course, makes it much faster to stream the data over the internet. And that's how we can basically get full utilization on our training GPUs while still streaming the data without having it all on our local computer. And then we create a commit in the dataset, which is total empty. And this is a little trick that we will see later why we do. We don't have to do this, but I like to do it. And then we're actually going to upload the data. And we do this with the Deep Lake compute functions, which allow us to parallelize it and make it much faster than if we would just iterate the images and upload them one by one to the dataset. So this function essentially takes a list of file paths as input, and it will create samples where we have appended a image, which we read with the Deep Lake read function. And we will append the images which actually have 3 color channels. Some of the images in this dataset are grayscale, so I chose to skip those because they aren't really valuable for my use case. And it tends to complicate things if the tensors have different dimensions. So this is basically what we need to do to upload the dataset. So thanks to the parallelization, this process should be quite fast. We can see down in the right corner here the number of samples that we have uploaded. So we have soon uploaded 1,000 images, and we have 3,500 in total that we're going to upload. Uploading the images took approximately 1 minute, which isn't too bad for a Wi-Fi connection and 3,500 images. So we can now see that the datasets appeared in the datasets folder in the Activeloop user interface. And here we can now explore the datasets. So this is all the images that we have uploaded, and we can look around and get a feeling for what the dataset actually looks like. And of course we can also look at the labels and the values of the different tensors in the dataset. So for example, if I press this image, we can see the size of the image. We can see that it has the label 1, which corresponds to positive label because it's a yellow vest. And we can see the name of the source file. And we can also show the different tensors overlaid on top of the image. So we can see that we have a positive, here we have a negative, and so forth. So the next thing we might want to do is to add more images. So this is the dataset as ingested from the Kaggle dataset, but typically you might want to complement with images which are more representative of your own use case. So that's the next step I'm going to do. And here we can see that I have another folder with images, just a few images in this case, but they are images that I deem to be more representative. So I want to upload them and concatenate them to the dataset that we have now. And before we do that, we can talk a bit about versioning. So when uploading the dataset, we did 2 different commits. And if we go to the version control here, we have the different branches. So far we just have the main branch, but we also have the different commits. And here we have the empty commit that we did first when creating the dataset, and then we have the commit we did after uploading the images. So if I press the empty commit, then we can see that we have no data because we did it before uploading data. And if I go to this one, we have the all the samples. So just by pressing the different commits here, we can easily go back and forth to different points in time and see what the dataset looked like in that specific time. And that means that if we accidentally do something bad to our dataset, we can always go back to an earlier version of it. So we don't have to try to understand what did change in the dataset without having the old state saved. But for now, let's go back to our new images and upload them. To do this, I have another script which is called add images, and this is mostly the same as the first script. The main difference is that we load the existing dataset, and then we're checking out the empty commit before adding all the images. And we're also branching out to a new branch from this empty commit. So the reason we do this is that I like to see what images I'm actually uploading before I merge them into the big dataset, because then they tend to disappear and be hard to see that you actually did the right thing. So let's run this script. Okay, so now our images should be uploaded to the dataset. And here we created a new branch. So if I go to branches here and refresh the page, I can see that I have my new feature branch, add more images. So if I press this one, we can see that we have 11 images that we uploaded to this branch. And I can look at the different images. So this is a good way to make sure that everything looks as you intend it to do before you upload anything. And what I can see here is actually that I have a duplicated image here. This image is the same as this image. So let's do a grid like this, and we might see it easier. So we have the 0th index is the same image as the 6th index. So let's fix this before we merge it, so we can remove the 0 index. So we do this by loading the datasets. And we can show the different branches. We check out the feature branch. And then we pop the 0th example. So this should now remove this image and make sure that we don't have any duplicates. And then I can make a new commit on this. So if I now reload the page, I can see that I just have 10 images. And we no longer have any duplicates. So this looks good. We can also see on the commit history that here is my commit, which removed the last image. So what I want to do now is that I actually want to merge these 10 images into my master branch, or my main branch. So right now we can see that we have 3,479 images on that branch. So let's check out the main branch. And then we do merge with the feature branch. So now we will merge in these 10 images into our main dataset branch. And we should end up with 3,489 images instead, as soon as this is done. Okay, so let's refresh. And we see that we have 3,489 images. So now our new images is added. And we can probably see them here at the end of the dataset. So if we go back to the branches and look on the main branch, on the commits, we can see that now we have a merge commit. So the next thing we might want to do is to improve the quality of the dataset. So if we look at the different samples here in the dataset, we can see that a lot of the images contain these kind of marketing images where the background has been cropped away. And almost all of these images, at least it's my suspicion that they correspond to the positive class. So it's mostly yellow vests or hard hats that has white background. And that would surely be confusing for the detector and not at all help the detector in solving the problem we actually want it to solve. So the first thing we're going to do here is to try to automatically filter away some of them. And then we might need to actually do some manual annotation to get rid of these images. But let's start with doing automatic filtering. So I have a script here called filter images. And what we do here is that we define a compute function which will be applied to all the images. And this function downloads the image as a NumPy array. It sums up the number of total white pixels in the image and divides by the total number of pixels in that specific image to get the ratio of how many percent of the pixels are white in the image. And then we append that to the output sample. And this function is called for each sample in the dataset. So we load the dataset and we branch out a new branch from the empty commit, and then runs this function on all the images on the main branch and outputs them to the new branch. So this will create a new branch which contains the same images as the main branch, but with the ratio of white background added. So let's execute this function. So this will take a little bit more time because now it needs to stream all the images from the server and calculate the values for each pixel in the image. But thanks to these compute functions, it's really easy to do it parallelized. So we have 8 different workers that is actually doing this in parallel. So it should be relatively quick on our 3,500 samples dataset. So that was not too bad, a bit more than 1 minute to go through all the images. And now we should have a new branch in our dataset. So let's refresh the page and look at our different branches. So yes, we have the debug branch with the white background aspect ratio. So we can see now that we have a new tag on each of the image with a ratio of white pixels. So this, for example, has a much white background and a high value, 43% of the image is just white, while this one is very, very low. So what we can do now is that we can sort these different images by this value. And we can see how it looks like. So up here we have images with very few total white pixels, and down here in the end we have the ones with very much white background. So we can see that it's almost only the equipment that is down here, not any regular images. So this is why we want to remove this. So if we go up a little bit, we can see this is probably the first. Let's see, where did we had one regular image. There we have one regular image which we probably want to keep. And here we have one. So this is probably the first image that we actually want to keep in our data set. So this image is number, or rather we have 46% white ratio on this one. So if we choose the cutoff point as 46%, we would get rid of quite a lot of these images, but we still would have a lot of them in our data set. So let's be a little bit more aggressive in this case, since I don't want to do a lot of manual cleanup afterwards. So I think we can go even further. Something like here, we start to see a lot of normal images. So let's take this image as our cutoff point, and here we have 18%. So we can go back to the query engine, and we select everything where white ratio is larger than 0.18. And now we can do a quick check that this seems reasonable. More or less everything we sort away are these bad images, and we can of course flip it the other way around and see how many of these white background images are we actually still having left in the data set if we use this cutoff point. So we can see that there is a bit of them. But let's use this number for now. So what we also can do is that if we open the IPython terminal again, and we import DeepLake, we load the dataset, and we check out the branch which is called debug white BG ratio. Then we can actually do a query, the same as we do here. So let's select everything that is more than 18% white background. And what we want to do now is that we want to look at what are the classes for this. So this will return a view of the data set, and then we can look at the labels. So now we have the different labels. We see that it's mostly one, that is protective gear that has white background. But we can import a counter class. And we can see that we have 526 of the protective gear class and just 9 of the other ones. So this is an indication that such a skewed slice of the data set would probably be very confusing for the model when we're trying to use it in training. Now when we have decided which frames we should remove, it is time to actually remove them from the master branch. So we have already verified that the selection we have done looks good. So optimally, I would prefer to do this on a feature branch and then merge in the feature branch to the main branch to delete the files from there. But we need to consider that the merge function is very new in DeepLake, and as of now it is not possible to merge removing objects. So we could do it when we added images. Then we could add image to a feature branch and merge in that branch, but unfortunately not now when we remove it. So instead we need to do it directly to the master branch. And I will do this by first checking out the branch where we have the threshold ratio calculated. And then I'm gonna, we could run a query, but we can also just use the tensor directly in NumPy to get the indexes of the images which has too much white background. So what we're doing is that we will address the white ratio tensor. We convert it to a NumPy tensor, and we say that we want all indexes where it is less than 0.18. And we're going to pass this to the NumPy where function so that we get the index IDs. So here we have the IDs that we should remove. So we check out the main branch where we will remove the frames. And now we need to use the pop method to pop each of the frames that we don't want to keep. And as of now, this is the only way to remove multiple frames from a dataset. And it is a bit slow, so we will probably need to wait a few minutes for it to work. So what we need to do here is also that we sort the indexes in reverse order. Since we pop by index, we need to start from the end, otherwise the indexes will change after we have popped the first ones. So now we just need to sit back and wait for a few minutes, I would guess. So I just realized my mistake. When selecting the frames to remove, instead of removing the ones with more than 18% white background, which we were supposed to, I accidentally flipped operator and removed the ones without much white background. Which means that I have currently removed 149 images which I was not supposed to remove. So I'm gonna abort this. And if we didn't have version control now, this could be a catastrophe, which could be really hard or impossible to regain from. And we can also see here in the user interface that we have now on the master branch, we have just 3,347 images. So we lost a lot of good images, but thankfully, since this is version controlled, we can see that this is the uncommitted head, and of course we can in the UI get back to the last commit where we had the correct frames, but we can also see here in the diff that we have removed the samples, and now we can just do a reset to remove the changes right down to the head and reset this branch to the last commit. So this will effectively reintroduce all the images I accidentally removed. And after doing this, we can just kick off a new job, making it correct. So we have our to remove list, which contains all the images which should, or the IDs of the images which should not be removed. So we can do to remove equals set of to so we want all the IDs in the data set minus the ones that we actually should keep. So now we have 535 images instead, which is indeed correct. So now we can start over and actually remove these frames from the master branch. Okay, so the images has now been removed from the main branch. We can see that we just have 2,955 images now. And while I was on it, I also made a new commit on changing some of the images which I thought was bad in some way or another. So after a while, when we have a lot of commits being stacked up on top of each other, it might be hard to get an overview on what has actually changed on this branch throughout the commits. So for example, since this commit when we uploaded the images from Kaggle, what are all the changes we have done up to this point on the main branch? And for this I have created another script. So this script will take two different commit hashes that we get here from the user interface or from the dataset.commits in the API. And it will check out each of the two commits, check what files are located in that commit, and then calculate what files have been added, what files has been removed. And it will also calculate the hash value for each frame that exists in both of the commits and see if the hash of the actual image has changed. So then it will be marked as modified. And we do this on a new branch that we check out. So I do this in 3 different steps. I first create a new branch with all the new images that has been added in commit 2 from commit 1. I then create a new branch which adds the images that has been removed, and then one branch with the images that has been merged. And these branches all have the same tensors as the main branch, plus 2 new tensors, one change tensor which contains the actual type of modification, so added, removed or modified, and one images new, which is used in the ones that are modified, so that we can see both the old value of the image and the new value of the image, so we can compare them side by side. So I will run this script, and the first commit will be the one where we uploaded the images from Kaggle, and the second commit will be this latest commit on the main branch. So this script will take a while now, since it needs to go through all the images and calculate the hash values of them. So it will probably take a few minutes, 10 minutes probably. So I pause the video for a while. So now that this script has finished and it has created a new branch, which we will be able to find here in our version control tab. So here we will see that 578 images has been changed, and most of them have been removed. We know that we have removed a lot of these white images, but we can use the query engine to select every image where the change is added. So here we see that we have 4 images that has been added, which is a bit suspect, because we were supposed to add 11 images. So this has already helped us find an issue. We can also select modified, and here we see that we have 46 images that are modified. So let's start from the top here. We can see this one looks very strange, and this is because I thought the image was a bit too bright, so I tried to reduce the darkness, and it seems like I have had an integer rollover issue. So we can deselect the new images and see how it used to look before and see the difference. So that's something that needs to be corrected, which I might not have noticed if I didn't use version control. This image, we can see that I removed the top of it because it contained a logo, which I didn't want to have included in my training data. And we can actually select single view here, and we can add a view, and on this one we select one of the images and we add another view, place it next to this one and select the images new. So here we will see the difference between the images. So if we save this one, and we also want to enable the change. So let's run this query again. So now we see all the difference in the images side by side. So a lot of them we can see that it's not any big difference, and I suspect this is due to the encoding of the images. I have made a change where the images got re-encoded, and there we have slight differences which will create a different hash for it. But we can easily go through here and see the ones that have changed significantly to verify that that change seems correct. I actually think we don't have the filter active. So now we only have 46 images, which has actually changed. So we see that this one needs to be corrected. This change seems reasonable. This image, I have flipped it because it was upside down, so that seems reasonable. Here we have something strange, two images that has been mixed up. So I probably tried to do something here that mixed up the images, and that might mean that the labels are actually incorrect on these images now. So that would be something I need to look into. So yeah, basically the point I want to make here is that when making changes to a dataset, especially large datasets where it's hard to get an overview of what you have actually done, then you need to have some way of visualize how the data differs and verify that what you thought you did was actually what you did in the end. So this is very useful, and in the next video we will have a look at how we can train our model on different branches and have different quality of test data sets that we evaluate on. And if we want to add more images to our test data sets, we can create a new branch and still do the evaluation on both the old branch to make it comparable, and then on the new branch to get numbers that we are actually more comfortable with or close to the truth. And we can also then upload the evaluation results to the images, just like we did with a weight ratio threshold here, and sort the images by prediction accuracy and so forth. So that will be very useful too. Before we end this video, I should mention that the merging that we have used it was just released a week ago or something, so you need to be on the latest version of DeepLake to use that. And the query engine that we have been using here, that's an enterprise functionality. So if you don't have the enterprise account, if you have a free account, then you won't be able to use the query engine on your own datasets, only the open Activeloop datasets. But you can still do everything that we have done. You just need to do it a bit more in the terminal and upload it as separate branches or commits, instead of having it as interactive and easy as it has been having the query engine here. So that's all for this video.